Have you ever had a strange, fleeting thought? Perhaps right as you were drifting off to sleep when everything begins to dim but hasn't disappeared yet. When you fall asleep, where do you actually go? We give it simple names: sleep, anesthesia, being out. But what really happens in that moment isn't that your body shuts down. Your heart keeps beating, your lungs keep breathing, and your brain remains active. What fades is something far more subtle: the sense of being you, your awareness, your presence, that quiet inner knowing of "I am here." For most people, this question is nothing more than a philosophical curiosity, something you might briefly wonder about and then forget. But for one man, it became impossible to ignore, because his entire profession depended on making that awareness disappear and then bringing it back again. His name was Dr. Stuart Hameroff, an anesthesiologist. Every day, Hameroff deliberately, precisely, and reversibly turned off human consciousness. He would watch patients talk, joke, and worry one moment, fully present. And then, as the anesthetic flowed, something unmistakable would dissolve. Not the body, not brain activity, but the spark of awareness itself, the personality, the sense of personhood. Later, when the flow of anesthetic gas was reversed, the person would return. Their memories were intact, their identity unchanged. There was no sense of time passing at all. From the outside, it looked routine, efficient, almost mechanical. But Hameroff was haunted by a detail most of his colleagues never stopped to question. No one really knew how it worked. Doctors knew that anesthesia worked. They had charts, dosages, and protocols refined over decades. They knew that certain simple, chemically inert molecules could reliably extinguish the flame of consciousness. But they didn't know where the light switch was. There was no agreed-upon location, no clear mechanism explaining why awareness vanished while the brain itself remained busy and alive. For Hameroff, this wasn't just a gap in medical knowledge. It felt like staring into an abyss. Because if you don't know how you're turning consciousness off, do you really know what consciousness is at all? That question refused to stay theoretical. It followed him into the operating room, into his research, and into the quiet moments when science stopped being abstract and started feeling personal. Anesthesia didn't behave like a blunt instrument. The body continued functioning. Vital systems stayed online. Neural signals kept firing. It was as if the orchestra was still playing. But the conductor had quietly left the room. And if that were true, then consciousness wasn't simply the noise created by neural activity. It wasn't evenly spread across the brain. It wasn't just a byproduct of complexity. It had a location, a mechanism, a deeper home. Finding that home would pull Hameroff far beyond the familiar boundaries of medicine, deep inside the neuron itself, and eventually into one of the most controversial ideas in modern science: the possibility that the human brain is not merely a biological computer, but something far stranger, something that may touch the deepest structure of reality itself. Hameroff's search for the switch that could turn consciousness on and off slowly pulled him away from the operating room and into deeper, less comfortable territory. At the time, the dominant explanation for anesthesia was surprisingly crude. The idea was that anesthetic molecules simply dissolved into the fatty membranes of neurons, disrupting their function until the system seized. In essence, consciousness was thought to fade because the brain had been sufficiently gummed up. Technically, this explanation worked. Conceptually, it felt hollow. It never sat right with Hameroff, because consciousness was not an ordinary biological function. It was the most complex phenomenon we know of. How could something so refined be switched off by something so blunt and indiscriminate that discomfort pushed him to look deeper? Instead of focusing on the synapses, the junctions between neurons that had dominated neuroscience for decades, Hameroff began to explore the inner world of the neuron itself. Inside every neuron is an intricate internal skeleton, composed of tiny hollow cylinders called microtubules. For most neuroscientists, these structures were little more than cellular scaffolding, the internal beams and transport rails that kept the cell intact and organized. They were important for structure, but irrelevant for thinking. Hameroff saw something very different. He noticed that microtubules are built from repeating units of a protein called tubulin, arranged in a precise and highly ordered lattice. More importantly, each tubulin protein can exist in more than one physical state, subtly shifting its shape back and forth. To Hameroff, this looked eerily familiar. A system of elements that can switch between states is the foundation of computation. In other words, it resembled a binary system, a computer. He began to wonder whether each neuron might not be a simple relay station, but a sophisticated processor in its own right, performing deep computation far below the level of synapses. This idea offered an elegant solution to the anesthesia mystery. Hameroff hypothesized that anesthetic molecules were not randomly disrupting cell membranes at all. Instead, they were lodging themselves in small, non-polar pockets within the tubulin proteins. Once there, they would prevent tubulin from switching between states, effectively freezing the computational activity of the microtubules. Consciousness, in this view, wasn't being smothered by brute force. It was being precisely paused at its source. At the same time, across the ocean at Oxford University, another mind was circling the same mystery from a completely different direction. Sir Roger Penrose, one of the world's most brilliant mathematical physicists and a close collaborator of Stephen Hawking, had become convinced that the human mind could not be explained as a classical computer. In his 1989 book, The Emperor's New Mind, Penrose drew on the profound implications of Kurt Gödel's incompleteness theorems. Gödel had shown that within any formal mathematical system, there will always be statements that are true but cannot be proven using the system's own rules. A computer, bound by algorithms, can never escape this limitation. Yet humans routinely do. Through intuition and insight, we can recognize truths that no algorithm can formally derive. For Penrose, this capacity for non-algorithmic understanding was not a philosophical curiosity. It was a defining feature of consciousness itself. If the human mind can grasp truths that no classical computer ever could, then consciousness must be doing something fundamentally different. It must be harnessing processes that go beyond classical physics. It must, he argued, be tapping into quantum mechanics. But Penrose faced a problem of his own. Quantum processes are delicate and easily disrupted, and the brain is warm, wet, and chaotic. As a physicist, he had no idea where such processes could survive inside a biological system. He had the theory, but not the biology. Then, in 1992, he received a letter from an anesthesiologist in Arizona. Stuart Hameroff had read The Emperor's New Mind and felt he had found the missing piece. He told Penrose about the intricate, crystal-like structures hidden inside neurons. He described microtubules and their strange properties. And he offered a simple, provocative suggestion. I think what you're looking for is in the microtubules. The correspondence between Stuart Hameroff and Roger Penrose marked a turning point. What began as two separate questions, one rooted in medicine, the other in physics, slowly converged into a single, audacious idea. Together, They gave birth to one of the most detailed and controversial theories of consciousness ever proposed, the theory of orchestrated objective reduction, often referred to as OR. At the heart of this theory is a radical reimagining of how the brain works. OR proposes that the tubulin proteins inside microtubules are not passive structural components, but active participants in consciousness. In this model, tubulin proteins function as quantum bits, or qubits. Unlike a classical bit, which must be either a 0 or a 1, a qubit can exist in a superposition of both states at the same time. Rather than choosing a single outcome, it temporarily holds multiple possibilities at once. According to the theory, tubulin proteins enter these states of quantum superposition and become linked with neighboring proteins through a process known as entanglement. This allows a coherent quantum state to spread across large sections of a microtubule, forming a vast, unified quantum computation. Instead of information being processed step by step, as in a classical computer, many possibilities are explored simultaneously. The brain, in this view, is not merely calculating outcomes. It is sampling potential realities. This proposal immediately raises an obvious objection. Quantum states are famously fragile. They tend to collapse when disturbed by heat, moisture, or environmental noise. The brain, after all, is warm, wet, and biologically chaotic. How could such delicate processes survive long enough to matter? This is where the orchestrated aspect of OR becomes essential. Hameroff and Penrose argue that microtubules are uniquely suited to protect quantum coherence. Their hollow cylindrical structure may act as a natural shield, isolating the quantum states inside from environmental interference. Beyond passive protection, the cell itself may actively support and regulate these states, maintaining coherence through biological processes that function like fine-tuning mechanisms. In this sense, the quantum activity is not accidental. It is orchestrated. The cell behaves less like a noisy factory and more like a carefully managed concert hall, sustaining delicate patterns long enough for something meaningful to occur. But what happens to this quantum computation once it is formed? Penrose introduces one of the most unconventional ideas in modern physics. He proposes that quantum superpositions are not merely abstract probabilities, but real physical states that place space-time itself in a condition of tension. When a superposition grows large enough, when it reaches a specific threshold, it becomes unstable and collapses on its own. This process, which Penrose calls objective reduction, does not require an external observer. It is a fundamental feature of reality. According to OR, each such collapse corresponds to a moment of conscious experience. Consciousness does not emerge gradually or continuously. It arrives in discrete flashes, brief events where possibility resolves into experience. Penrose and Hameroff calculated that, under typical conditions, these collapses would occur roughly 40 times per second. Remarkably, this frequency aligns with gamma waves in the brain, long associated with focused attention and conscious awareness. While this correlation remains debated, it offers a striking point of contact between theory and neuroscience. If Penrose is right, the implications are profound. Consciousness is not something the brain creates in isolation. Instead, it is a process that connects the brain to something already woven into the fabric of reality itself. Each conscious moment, every insight, every emotion, every perception of color or sound is not merely an event inside the skull. It is also an event in the deeper structure of the universe. Penrose goes even further. He speculates that the outcomes of these quantum collapses are not entirely random. They may be influenced by information embedded at the most fundamental level of reality, a realm of mathematical truths, ethical principles, and aesthetic forms that exist independently of human thought. In this view, consciousness becomes a bridge between the physical brain and an underlying order that has always been there. Our brains are not simply generating experience. They are receivers, tuned moment by moment to a vast, cosmic symphony. Whether this vision ultimately proves correct remains an open question. But it offers something rare in the science of consciousness, a framework that does not reduce awareness to mechanical activity, nor dissolve it into mysticism. Instead, it places consciousness at the intersection of biology, physics, and meaning, a process grounded in the body, yet open to the deepest structures of reality. At this point, it's natural to ask a quieter, more personal question. If this view of consciousness has any truth to it, how does it change the way we live? The answer is subtle, because this isn't a physical exercise, and it isn't a technique you need to master. It's a shift in perception. The practice, if it can be called that, is simply to consider the possibility that your consciousness is not something sealed inside your skull, but something that may be receiving, tuning, and participating in a larger field of reality. Most of us move through life assuming we are isolated minds, generating thoughts on our own, sealed off from the world except through our senses. But the framework we've been exploring invites a gentler reinterpretation. Instead of seeing yourself as a separate thinker producing awareness, you can begin to see yourself as an expression of a conscious universe, one localized perspective within a much larger whole. This doesn't require belief. It only requires curiosity. Think about those moments of sudden clarity, the aha insights that seem to arrive fully formed. They don't feel constructed step by step. They appear, almost as if they surfaced from somewhere beyond deliberate thinking. Penrose would describe these moments as non-computable understandings that cannot be reduced to algorithmic processing. Through the lens of this theory, you might consider that such moments are not merely your brain working harder, but brief connections to deeper, non-algorithmic truths. Not something you forced, but something you received. The same perspective can soften how we understand moments of awe. When a piece of music moves you unexpectedly, or when you stand before a sunset and feel something quiet open inside you, there is a sense of resonance rather than analysis. You're not calculating beauty. You're responding to it. In the language of this theory, you could think of these experiences as your consciousness resonating with an underlying harmony in reality itself. Much like an instrument vibrating in sympathy with a larger field of sound. Seen this way, presence becomes more important than effort. Consciousness doesn't deepen because you strain to control your thoughts. It deepens when alignment naturally occurs, when attention, perception, and openness converge. Just as microtubules in the theory do not force quantum coherence but sustain the conditions for it. Your role is not to manufacture awareness, but to remain receptive to it. This reframing can quietly change how you relate to your inner life. Thoughts become signals rather than commands. Emotions become movements rather than problems to solve. Awareness becomes something that arrives, fades, and returns, rather than something you must constantly produce. Life begins to feel less like a system you are managing and more like a process you are participating in. None of this asks you to abandon science or reason. It simply asks you to hold a wider frame, to recognize that you may not be just a biological machine generating consciousness from complexity, but a conduit linking the physical processes of your brain with something more abstract, more universal, and still not fully understood. In that space between mechanism and mystery, consciousness stops feeling like a burden to control and starts to feel like a relationship, one that unfolds, moment by moment, as you remain open to it. This journey from the operating room to the quantum realm is one of the most staggering stories in modern science. It begins with a simple medical mystery and unfolds into a theory that challenges how we understand the mind itself. Orch. Or proposes that consciousness is not a smooth, continuous stream, but a sequence of moments like notes in a symphony, each one arising from quantum processes rooted in the very geometry of space-time. In this view, the mind is not a machine producing awareness, but a quantum orchestra, playing experience into existence moment by moment. It is important to be clear, however, that Orch-or remains on the controversial fringe of neuroscience. Most scientists are deeply skeptical, and for good reason. The brain's warm, wet, and noisy environment poses a serious challenge to the survival of delicate quantum states. The problem of quantum decoherence remains the theory's greatest obstacle, and no definitive experiment has yet resolved it. Skepticism here is not a weakness of science, but one of its strengths, and yet the theory persists. It persists because it dares to confront the hard problem of consciousness directly, rather than sidestepping it. And it persists because it makes specific, testable predictions, some of which have received tentative, though still inconclusive, experimental support. Whether these early findings will ultimately strengthen the theory or dismantle it remains an open question, and one that ongoing research continues to explore. What gives Orch-or its lasting power is not certainty, but courage. It refuses to reduce consciousness to a convenient illusion, and it refuses to treat subjective experience as an afterthought. Instead, it invites us to consider the possibility that awareness is woven into the deeper fabric of reality itself, and that the brain is uniquely structured to participate in that process. So where do you go when you fall asleep? Perhaps the question is not where you go, but what stops. Perhaps what we call you is a delicate quantum song, an orchestrated resonance linking the biology in your head to the physics of the universe. And when the anesthetic flows, the orchestra is quieted, the conductor lowers the baton, and the music fades into silence. It waits there, poised, until the moment the baton rises again and the music of consciousness begins anew. So what do you think is the idea of a quantum mind pointing us towards something real, or simply reminding us how much we still don't understand? Either way, it leaves us with a quieter, deeper question about what it means to be conscious at all.